Hello, good morning friends. Now we want to discuss about numerical methods. Numerical methods comes under engineering mathematics 4. As we know, or what we have discussed in the last session, suppose if I want to solve a second order differential equation, or in particular second order ordinary differential equations using fourth order Runge-Kutta method, what are the preliminary things required? Say for example, first I want to identify whether the given equation is an differential equation or not, or particularly ordinary differential equation or not. Suppose a differential equation containing dy by dx, d square y upon dx square, etc., then we can say that it is an ordinary differential equation. Then how do we recognize or how do we find out order of the differential equation? Highest derivative present in the equation is the order of the differential equation. Okay, so once we are able to identify the given equation is an ordinary differential equation with the second order. Now sometimes they will give an initial value problem. Say for example, they will give dy by dx is equal to f of xy with y of x naught is equal to y naught. So one initial condition. Now exactly in the similar way, so they will give second order differential equation with the initial conditions. So it means suppose if they give initial value, how do we find out the solution of such a type of problems? So we have seen in the last session, and I have also discussed about numerical methods. What are the numerical methods and what are the advantage of the numerical methods, right? So I think we have also discussed about Euler's method, first order Euler's method and second order Euler's method. Then I have given Runge-Kutta method. Runge-Kutta method means Runge-Kutta first order method, second order method. Now I want to solve second order initial value problem using Runge-Kutta fourth order method. Okay, so for example, they will give an equation of this type. So dy by dx is equal to f of xy. So it is a function of xy can be assigned to dy by dx means slope, right? So along with the condition y of 0 is equal to y naught. Sometimes they may give this condition in this form, y of x naught is equal to y naught, right? So we may ask why I want to use and fourth order Runge-Kutta method, or why we want to use a numerical method, right? So I think in the last session we have discussed this point. Say for example, they have given a differential equation. If we are unable to find out the analytical solution, then we will go for numerical method. Okay, so now I am going to use a numerical method. So they have given x naught is equal to y naught. So it means x naught value is known, y naught value is known. Now I want to find out, so what is the value of y1? How do we calculate the value of y1 corresponding to x1? Is it clear? And exactly in the similar way, we want to calculate x2 is equal to y2, or y of x3 is equal to y3, y of x4 is equal to y4, and so on. So by using this method, we can find out all those values. So using the following formula. So it is given that y suffix I plus 1 is equal to y I plus 1 by 6 times of k1 plus 2 k2 plus 2 k3 plus k4 into h. So we need this formula. Now in this formula, if I replace I by 0, I can obtain y1 corresponding to x1. Similarly, here also I can replace I by 0, right? Then I will evaluate, I can obtain the value of y1. So what are the values of k1, k2, k3, k4? So how do we calculate these constants? So k1 means it is a function of x and y. So f of xi, yi. As I have mentioned, if I replace I by 0, so I will get x naught and y naught. So what are the values of x naught and y naught? So in the given differential equation, they have given the initial condition. So x naught is equal to 0. So y naught value is also known. It means x naught, y naught are known. Now I will replace in the given function x by x naught, y by y naught. So right, I will estimate the value of k1. Similarly, I can calculate K2 is equal to I means I can replace I by 0 plus 1 by 2 times of h comma y suffix 0 plus 1 by 2 times of K1 into h. I know these values, I will substitute in the given function, then I can evaluate K2. And similarly, K3 is equal to function of x naught plus 1 by 2 times of h, y naught plus 1 by 2 times of, I want to use the previous value, namely K2 into h. I will substitute in the given function and I can evaluate K3. Similarly, I can obtain K4 is equal to f of x naught plus h yi plus I want to use the value of K3 into h. When I substitute in the given function, so these two coordinates, I can obtain K4. Then I will substitute these values in the above formula. I can obtain y1 corresponding to x1. So, like that we can obtain various values, then we can draw the graph, then we can analyze. Okay. Now, whatever I have explained, so these are the mathematical steps, right. So, you may ask graphically K1 means what, K2 means what, K3, K4 means what, or graphically what is the meaning of a fourth order Runge-Kutta method. So, now we will come to know the meaning of K1. Okay. Now, you know the values of x naught and y naught. I will substitute and I will evaluate. So, I can say that K1 means I will get the slope at xi. So, for example, now you are observing this graph. Initial position is this. I may call it as an xi. Say for example, now I want to move from this point to this point. I can say that, so this point is xi plus h. H is what? Say for example, I want to move from this point to this point, some time is required. So, I can say that h is the time, right, or step time. Suppose if I want to reach from point number 1 to final point, initial point to final point, right. So, now I want to calculate middle point at half time. That is why I can say that xi plus h by 2. Okay. Now, K1 means it is the slope at this point. So, I can calculate the slope, what you are observing, the dotted line. So, this represents a slope corresponding to xi. So, that is the geometrical meaning of K1. Exactly the similar way, now you want to calculate K2. As I have mentioned, so you know the function, in the function you can replace x by x coordinate, y by y coordinate, and you know that we want to use the previous value, namely K1, right. So, geometrically what it represents? So, this is an estimation of the slope at the midpoint of the interval xi plus 1 using the Euler's formula. Now, as I have mentioned, so this is the initial point, final point. Now, I want to calculate midpoint after half time. How we are going to calculate? So, using this formula, right. So, you can obtain above this line, dotted line is represents the slope of the function at xi plus h by 2. Okay. Now, similarly, you can calculate K3 by replacing x coordinate and y coordinate. So, this is an improved Euler's approximation for the slope at midpoint. So, at this point, so you can calculate, I hope you are observing, so one more dotted line. So, that is the K3, right. So, now finally, we can obtain K4 at xi plus h. K4 is equal to, so this is a Euler's method, slope at this point. So, it means what we are observing slope. So, it means we can calculate slope at the initial point, slope at final point and slope at middle point. How many slopes are there? Oh, totally 1, 2, 3, 4. Now, I want to take the average of these slopes. So, what we have written in the previous slides, yi plus 1 is equal to, right. So, that is the average of all the 4 slopes, or sometimes we can say that weighted averages of K1, K2, K3, K4, that represents the final value. So, the fourth order Runge-Kutta method is similar to the Simpson's rule. We are already familiar with the Simpson's method or Simpson's rule. So, we can compare this method with Simpson's rule. A sample of the slope is made at the midpoint of the interval as well as the end points, and a weighted average is taken, placing more weight on the slope at the midpoint. As I have shown in the previous graph, we have calculated K2 and K3 at the midpoint. That is the meaning. So, it should be noted that Runge-Kutta refers to an entire class of initial value problem solvers, which includes Euler's method and Heinz method. We are looking at one particularly effective yet a simple case. Okay. Now, I want to consider a particular example. How do we find out the solution of this example using fourth order RK method? So, they have given a first order differential equation f of t plus y of t naught is equal to y naught. So, t is represents time and position, is it clear? So, at a particular time, what is the position? Y of t. So, they have given initially y of t naught is equal to y naught. So, if you want to estimate at time t1, what is the new position? So, for that reason, we want to set h. H is equal to t1 minus t naught. H means it represents a time step. So, remember that f of t comma y, here t means time, y means position, gives the slope at the point t comma y. Thus, we can find the slope at t naught y naught. So, it means t naught is known, y naught is known. They have given a function of t and y. Now, I will replace t by t naught, y by y naught. Then I will substitute in the given function. Okay. Now, I will obtain k naught. Here I have written k naught. In the previous slides, I think I have written k1. In some textbooks, they have written k naught, k1, k2, k3, or in some textbooks, they have written k1, k2, k3, k4. So, we can use different annotations like this. Okay. So, we use this slope to estimate y of t naught plus h by 2. You will get a new position. You know the value of y naught plus h by 2 k naught. K naught is also known. So, when we substitute these two values, so you can obtain this value and sample the slope at this intermediate point. So, k1 is equal to f of t naught plus h by 2 y naught plus h by 2 times of k naught. So, you will get a intermediate point or midpoint. Okay. So, using this new slope, we can estimate y of t naught plus h by 2, approximately y naught plus h by 2 times of k1. K1 can be used to estimate, so this position, right. And similarly, so you can calculate k2, f of t naught plus h by 2 comma y naught plus h by 2 k1. Finally, we use this last approximation of the slope to estimate y of t1, t naught plus h, that is equal to y naught plus h into k2. The sample, the slope at this point is k3 is equal to f of t naught plus h, y naught plus h into k2. Okay. So, it means we have obtained all the 4 slopes, namely k0, k1, k2 and k3 approximate the slope of the solution at the interval t0 and t1, and therefore, we take the following weighted average. Therefore, we approximate y of t1. I have already given this formula. So, you want to substitute all the slopes in this formula, then we can obtain the new position using fourth order Runge-Kutta method. Okay. So, now you can represent our solution by a graph. To view this graphically, let us consider initial value problem. So, they have given y is a function of t. So, is equal to, it is given that 1 by 2 times of y of t minus t plus 1 with the initial condition y of 0 is equal to 0.5. It means at time t is equal to 0. What is the position? Position is 0.5. The following figure shows Euler's approximation of y of 1. That is, the following is the slope. It means k naught is the slope. They have given a function t naught is known, y naught is known. You can substitute and simplify. So, you will get 1.25. So, we get that y of t naught plus h by 2 is equal to approximately y naught plus 1 by 2. H is known, k naught is known. You can substitute. So, after substitution, we may obtain 1.125. 0.5 plus 0.5 into 1.25. Is it clear? So, when we draw the diagram, I think in the last session I have shown. So, dotted arrow represents slope field or direction field. So, we can draw the direction field of the ODE. Is it clear? Right. So, I hope now you are observing the blue color line and one more straight line that represents the slope. Right. So, what we have obtained y 0.5 means it lies between 0.4 and 0.5. So, t is equal to 0.5. What is the corresponding value? 1.125. I hope it lies between 1 and 1.2. Is it clear? So, this is the slope what we have calculated. So, you can say that Euler's approximation to the value of at t is equal to 0.5. So, we have obtained this position, right. So, now we want to move further. How do we calculate? So, that is the question, right. So, okay, now I want to calculate k1, right. So, I know all the values, t naught is known, h is known, y naught is known, k naught can be used. Is it clear? Again h is also known. I will substitute all these values. You will get a function of 0.5 comma 1.125. So, after simplification and I can obtain 1.0625. Is it clear? So, corresponding to these values I can obtain k1. So, k1 is also a slope. Now, you are observing a slope line. So, that is an improvement, right. Okay. So, we have obtained corresponding to 0.5. So, 1.03125 corresponding to 0.5 means I hope you will get this slope that can be observed in this graph. So, similarly, we can calculate k2, replace x coordinate by 0.5 and y coordinate by 1.03. So, it means I am using so k1 to estimate k2. So, finally, after simplification I can obtain 1.015625 and again this represents the slope with a golden line, golden straight line what we are observing corresponding to 0.5. So, we have obtained the slope. Okay. So, finally, you can calculate y at 0.1. It means we can obtain the new position. So, you know the values, you can substitute. After simplification, I can obtain 1.515625. So, what we are observing this line, golden color line. So, that is the slope corresponding to 0.1. So, it is the new position. Similarly, you can calculate k3 corresponding to these values. X coordinate can be replaced by 1 and y coordinate can be replaced by. So, this value in the given function, substitute and simplify. After simplification, we may obtain 0.757812. Is it clear? So, I hope you are observing a purple color straight line. So, this represents the slope corresponding to this value. Okay. Now, we want to obtain y1 is equal to, it means so far we have obtained all the slopes. You can substitute and you can simplify. So, you will get after simplification 1.52734375, right. So, what we are observing. So, this is the slope. Okay. Now, we have obtained the solution of the given differential equation. So, suppose if they give a differential equation in this form. Here it is given that dy by dx plus 2y is equal to 1.3 into e to the power minus x, or in general the given equation may be in this form, dy by dx is equal to a function of xy. So, here function of xy means what? You can take the right hand side function. So, for example, it can be written 1.3 into e to the power minus x minus 2y. Here y of 0 is equal to 5 is the initial condition at time t is equal to 0. So, what is the position? So, that is the meaning of this initial condition. Okay. So, now so far we have discussed about if they give an ordinary differential equation, especially first order ordinary differential equation, how do we find out the solution using fourth order Runge-Kutta method? So, my aim is to solve second order differential equation, but if we know how do we find out the solution of first order differential equation using Runge-Kutta method, so very easily we can find out the solution of second order differential equation. So, you may ask how do we say that it becomes an easy, or how do we say that? So, if you know first order solution by using RK method, how do you find out second order differential equation? Because second order ordinary differential equation can be converted into system of simultaneous differential equation. So, it means second order can be reduced to first order differential equation, then method is similar to the previous one. So, that is why I have solved one or two such type of examples. Okay. Now, I want to think about how do we solve simultaneous first order differential equations, right. So, for example, the simultaneous differential equations may be of the type dy by dx is equal to f of x, y, z. In the earlier case, it is given that dy by dx is equal to function of x, y, right. So, another equation is dz by dx is equal to a function of x, y, z. So, it means here x, y, z represents x is the time, y is the position and z is the velocity. So, that is the meaning of function of x, y, z. Okay. Suppose if the given equations may be like this, or given second order differential equation can be reduced to this form, how do we find out the solution? Using first I wanted to give using Picard's method, how do we find out? So, you know the Picard's formula. So, yi is equal to, or I can say that y1 is equal to y naught plus integration of function of x, y naught in comma z naught with respect to x. Similarly, corresponding to this function, you can use this formula. So, z1 is equal to z naught plus integration of some function of x, y naught, z naught with respect to x, right. And exactly in the similar way, y2 is equal to y naught plus integration of function of x comma y1 z1 dx. y2 is equal to z naught plus integration of function of x y1 z1 dx, and y3 is equal to y naught plus function of x y2 z2 dx. z3 is equal to z naught plus integration of function of x y2 z2 and so on. So, using this formula we can find out the solution by Picard's method. Okay. Suppose they are given a differential equation, we can find out the solution by using a Taylor series method. Here also assume that they have given second order differential equation, we have reduced second order to first order simultaneous differential equation. So, what is the method? So, method is Taylor series method. So, because why I am giving all this formula, when we want to solve a second order differential equation, we will convert second order differential equation into first order simultaneous equations. We want to solve same equations by using Milne's method. Some starter values can be calculated either by using Taylor's method or by using Picard's method. Okay. Here they have given two simultaneous equations. How do we solve? Now, I want to use Taylor's method, right. So, we are already familiar with the Taylor's method. So, Taylor series is y1 is equal to y naught plus h into y naught single prime y naught. It means you want to differentiate the given function, right. So, you will get first derivative replace x by x naught. How we are going to denote it? By y single prime with suffix 0 plus h square by 2 factorial. You want to differentiate the given function how many times? 2 times. Then you want to replace x by x naught. I hope you will get the value. Similarly, plus h square by 2 factorial y triple prime. So, it means you want to differentiate the given function how many times? 3 times. Replace x by x naught. Sorry, it should be h square by 2 factorial, h square by 3 factorial, and the next term is h to the power 3. So, it is square, cube and 4 and so on. H is goes on increasing. There is a small correction. Exactly in the similar way. So, z1 is equal to z naught plus h into z dash or z single prime. So, it means you want to find out the derivative of this function. Similarly, second derivative, third derivative and so on. Then you can substitute in this formula h square, h cube, h raised to 4 and so on, right. I will differentiate, I will substitute, then I will get the solution of the first order differential equation. As I have mentioned here, y naught single prime, y double prime, y triple prime, right. So, z single prime, z double prime, z triple prime and so on. We can find out all the derivatives of the both of the functions. Then I will substitute in these two formula and I can obtain the y2 and z2, and similarly you can obtain y3 and z3, right. So, y1 and z1 are known. So, we can calculate all these things, substitute in 5 and 6, we get y2 and z2, right. Similarly, if you want to calculate y3 and z3, y4 and z4, then you can draw the graph and you can compare. Okay. So, suppose you assume that they have given a simultaneous equations or they have given second order differential equation, we have reduced to first order simultaneous differential equation. Now, I want to use Runge-Kutta method. So, in our syllabus they have mentioned Runge-Kutta method. So, now I want to solve second order differential equation using this method. So, how do we find out? So, we are already familiar with ODE can be solved using RK method, right. So, I want to calculate the slopes, as I have mentioned, I want to calculate K1, K2, K3, K4. So, you know the function how we have solved in case of first order differential equation. Exactly in the similar way, now I want to calculate starting at x naught, y naught, z naught and taking the step size x, y, z, right, to be h, k, l respectively. The Runge-Kutta method gives. It means, so you will get two simultaneous equations. So, for first set you can take x, y, z. For the second set you can take h, k, l. Okay. Now, I want to calculate K1, h into h means step length, or as I have mentioned, right. So, h into f of x naught, y naught, z naught. Similarly, L1 is equal to h into some function of x naught, y naught, z naught, and K2 is equal to h into function of x naught plus 1 by 2 times of h, y naught, right. And similarly, I want to calculate y coordinate 1 by 2 times of K1. K1 can be used to estimate K2, right. So, z naught plus, so 1 by 2 times of K1, right. And similarly, I can calculate L2 using this formula, right. So, K3 can be calculated. So, L3 can be calculated, K4 and L4 using all these formula. Now, I want to use all these values in the formula. Y1 is equal to y naught plus 1 by 6 times of K1 plus K2 plus 2 times of K3 plus K4. It means you can take the average of all the slopes. Similarly, you can take the average of all these slopes, you can substitute. So, you will get so y1 and z1. So, it means initially they have given x naught and y naught. So, you can calculate so y1 and z1, right. So, to compute y2 and z2, we simply replace x0, y0, z0 by x1, y1, z1 in the above formula. So, we will get next step values. Okay. Consider the second order differential equation d square y upon dx square is equal to function of x, y divided by dx. So, the general form of the given equation may be in this form. Now, I want to reduce this equation into first order simultaneous equations. So, for that reason I want to replace d square y upon dx square by, or I can replace dy by dx by z. Then this equation, it means given equation becomes dy by dx is equal to z. It can be written as d square y upon dx square can be written as d by dx of z, that is equal to function of x, y dy by dx. So, it means, so first variable represents time, second variable say y represents position, and dy by dx represents speed with respect to time, or what we can say that velocity. Okay. Now, we want to consider one simple example, namely d square y upon dx square is equal to x y single prime whole square minus y square. So, they have given a differential equation. It is an ordinary differential equation. What is the order of this differential equation? Order is 2, because highest derivative present in the equation is d square y upon dx square. So, they have given at x is equal to 0.2, correct to 4 decimal places. Initial conditions are x is equal to 0, y is equal to 1, y single prime is equal to 0. So, it means that now I want to find out the position. It means new position at t is equal to 0.2, right. So, at time t is equal to 0, what is the position? Y is equal to 1, right. So, what is the new position corresponding to t is equal to 0.2 we want to obtain. How we are going to obtain? Using a Runge-Kutta method. Okay. So, now I am going to consider dy by dx is equal to z, that is equal to function of x, y, z. Then given equation can be written as dz by dx is equal to x into y single prime means z square minus y square. So, it can be treated as a function of x, y, z. As I have mentioned, so here x is the time, y is the position, z is the velocity. Is it clear? So, they have given initial condition x naught is equal to 0 and y naught is equal to 1, z naught is equal to 0 and step length is equal to 0.2. Okay. Now, we using these values you want to evaluate or you can estimate k1, k2, k3, k4 for the function x, y, z. Similarly, I want to estimate L1, L2, L3 and L4 for this function. Okay. Now, you know the formula k1 is equal to h into f of x naught, y naught, z naught. So, x naught is known, x naught is equal to 0, y naught is equal to 1, z naught is equal to 0 and we know the function of x, y, z. So, in that function I can substitute all the values and I can, after simplification, and I can obtain 0, right. And similarly, so you know the function I want to obtain L1. So, using the known values I can substitute in the given function, x can be replaced by x naught, y can be replaced by y naught, z can be replaced by z naught. Then after simplification I can obtain minus times of 0.2. Okay. Exactly in the similar way I want to calculate k2. So, you know the formula, we know all these values, x naught is known, h is known, y naught is known, right. So, k1 just now we have obtained, I can use the value of k1 to calculate k2 and similarly, so these values are also known, I can substitute and after simplification I can obtain minus times of 0.02, right. Oh, now I want to calculate L2. So, L2 means h is known, x naught is known, right. So, all these values are known. I will substitute these values in the function and I will simplify. After simplification, I can obtain minus times of 0.1998. So, that is the numerical value. Similarly, I want to calculate K3. K3 is equal to, you know all these values, you want to substitute numerical values, right, and simplify. After simplification, I can obtain minus 0.02. Similarly, L3. So, these values are known. Here I am going to use the latest value of K2, right. So, I will substitute and I will simplify. I can obtain minus 0.1958. Okay. How do we calculate K4? So, formula is known. All these values are known values. I will substitute in the given function and I will simplify. So, you will get minus times of 0.0392. Similarly, L4 is equal to, so formula is known, these values are also known. I will substitute the numerical values, then I can obtain a numerical value minus times of 0.1905. I will substitute all the slopes as I have mentioned, K1, K2, K3. I want to take the average, right. So, what is the average value? 0.9801 corresponding to the first function. Similarly, corresponding to the second function, I have obtained average values, namely L1, L2, L3, L4. I will substitute all the values and I will simplify. Finally, I can obtain minus times of 0.1970. Then if I want to, I can draw the graph of both of the functions, then I can compare, right. So, exactly in the similar way, now I want to consider and another second order differential equation. So, now I want to solve this example by using another method, namely Milne's method. So, what they have given? Y double prime plus x into y single prime plus y is equal to 0. So, with the initial condition y of 0 is equal to 1. So, it means x naught is equal to 0, y naught is equal to 1, y single prime of 0 is equal to 0. Obtain y for x is equal to 0, 0.1, 0.3 by any method. Further, continue the solution by Milne's method to calculate y at 0.4. So, as I have mentioned here, t represents time or x represents time. They have given initial position. Now, we want to find out the final position at t is equal to or at x is equal to 0.4. How do we calculate? So, that is the question. Okay. So, now first I want to convert second order differential equation into first order simultaneous equations. For that reason, I am going to replace y single prime by z. Okay. Now, in this equation, I am going to replace y single prime by z. The given equation can be reduced to y double prime, means it can be written as z single prime plus I will write x as it is, y single prime can be replaced by z plus y as it is equal to 0. So, you will get two equations, one is y single prime is equal to z and this is another equation, I will call it as an equation number 1. So, now I want to calculate starter values at x is equal to 0, 0.1 and 0.3 by using any method. Here I am going to use Taylor series method to find the value of y, right. So, now I want to differentiate the given equation how many times? N times. What is the given equation? So, this is the given equation. So, it can be differentiated how many times? N times. So, you know the formula. Which formula? So, Leibniz formula. By using Leibniz formula, it can be differentiated n times and finally, after simplification, I can obtain this equation yn plus 2 plus x into suffix yn plus 1 plus n into yn plus yn is equal to 0 at x is equal to 0. So, this can be simplified and obtain this equation. It means, so this term becomes 0 when we replace x is equal to 0. So, therefore, yn plus is equal to, I can take these two terms other side or a right hand side, right. So, here yn is common and what is the coefficient? N plus 1. So, that is why I have written yn plus 2 at x is equal to 0. I can obtain minus times of n plus 1 into yn at x is equal to 0, right. So, now I want to obtain all these values. So, y at x is equal to 0, what is the value? So, they have given initial condition, right. Then I want to obtain the second derivative I can replace x by 0, simplify, you will get minus 1. So, fourth derivative, right. So, replace x by 0, simplify, after simplification you will get 32. Sixth derivative, then replace x by 0, I can obtain minus times of 15, and similarly y1 at x is equal to 0 is 1. So, if you obtain third derivative, right. So, differentiate 3 times, replace x by 0, simplify, you will get equal to 0. Fifth derivative, differentiate 5 times, then replace x by 0, simplify, you will get equal to 0. So, it means when we observe these things, we will come to know third derivative becomes 0, fifth derivative becomes 0, seventh derivative becomes 0. Then we can substitute all these values in the series corresponding to y of x. So, you will get y of 0, x into y1 of 0, x square by 2 factorial, y2 of 0, similarly x cube by 3 factorial, y3 of 0. Just now we have calculated all these values. We want to substitute those values in this series, and we have to simplify, or y of x is equal to 1 minus y of 0 is equal to 1, y1 of 0 is equal to 1, right. So, exactly in the similar way, if you substitute in this series, we can obtain an equation 2, and similarly corresponding to the values of y of x. So, you can obtain z of x is equal to, or y single prime of x is equal to minus x plus 1 by 2 times of x cube minus 1 by 8 times of x to the power 5 and so on, that is equal to minus times of x into y. So, it means we can obtain equation 3, right. So, from equation 2, now I want to obtain y at point 1. So, y at point 1 means you know this series. In this series, wherever x is there, replace x by point 1. So, it means y of point 1 is equal to 1 minus point 1 square divided by 2 factorial plus 3 times of point 1 to the power 4 divided by 4 factorial and so on. So, when we simplify, I hope we will get 0.995. So, exactly in the similar way, now I want to replace x by 0.2. Wherever x is there, replace x by 0.2 whole square, 0.2 to the power 4 and so on. Substitute and simplify. So, you can obtain 0.9802, right. So, now I want to replace according to the given example, I want to calculate up to 0.3, x is equal to 0.3. So, in this equation, replace x by 0.3 and simplify. So, you will get 0.956. Okay. Exactly in the similar way. So, now I want to replace all these values in equation number 3. Zx can be replaced by 0.1, simplify. So, I can obtain minus times of 0.0995. Again, I can replace x by 0.2. So, simplify. So, you will get minus 0.196. Again, I can replace x by 0.3. What is the corresponding value? Minus times of 0.2863. Okay. Also, we can obtain from equation 1. So, z of x is equal to, you can take all other terms to the right hand side, you will get minus times of xz plus y. So, now you want to calculate z single prime at x is equal to 0.1. So, it means you know the value of x at 0.1, z at 0.1. You want to substitute those two values in this equation. Y is also known at 0.1. Just now we have calculated, right. So, you want to substitute and simplify. After simplification, you can obtain minus 0.985. Similarly, in this equation, we want to replace x by 0.2, x at 0.2, z at 0.2, z at 0.2 means this value. Is it clear, right? And y at 0.2 is also known. You want to substitute all these values in this equation, and you can obtain z single prime at 0.2. After simplification, you will get minus 0.941, right. So, in the similar way, I hope we can obtain z single prime at 0.3. You know all the values, z at 0.3, y at 0.3, right. Substitute and simplify. So, finally, you can obtain minus times of 0.87. Okay. So, now we want to substitute these values in this series. So, z at 0.4 is equal to z at 0, right. So, z single prime at 0.1, z single prime at 0.2, z single prime at 0.3. Just now we have obtained all these numerical values. So, you want to substitute the numerical values in the formula and you can simplify. So, you will get the Milne's predictor value, right. So, Milne's predictor value. So, exactly in the similar way you can substitute y at x is equal to 0, y single prime at 0.1, y single prime at 0.2, y single prime at 0.3. So, substitute in this formula and simplify, we can obtain 0.9231. So, these two formula we call it as an Milne's predictor formula corresponding to z and y, right. So, exactly in the similar way we can obtain y single prime at 0.4. So, you know all the values, substitute and simplify, you will get minus times of 0.7754. Okay. So, now exactly in the similar way we want to calculate Milne's character formula corresponding to z and y. So, z at 0.4 is the formula, z at 0.4 plus h by 3 z single prime 0.2 plus 4 times of z single prime 0.3 z single prime 0.4. So, we have obtained all these numerical values. So, I can substitute those numerical values in the formula and simplify. So, you will get minus times of 0.3692. Corresponding to y is formula is character formula is y at 0.2 plus h by 3 y single prime 0.2 y single prime 0.3 plus y single prime 0.4. Here I should write plus sign or minus sign according to the formula. Then you can simplify. I hope you will get after simplification 0.9232, right. So, y at 0.4 is equal to 0.9232 and z at 0.4 is equal to minus times of 0.3692 are the character values. So, like that you can obtain predictor and character values. Okay. So, now here also they have given one second order differential equation y double prime plus y into y single prime plus 3y into sin x. So, it can be reduced to simultaneous differential equation by replacing some other variable. In the previous examples, I have replaced dy by dx by z, not necessarily z. You can use a variable like u or u1, u2 or any other variable. So, this equation can be reduced to first order simultaneous first order differential equations like these two examples, and you can solve these two examples, right. So, by using fourth order RK method, then you will get the various values as I have mentioned x naught, y naught, x1, y1, x2, y2 and so on. Then you can draw the graph. Here you are observing two graphs with red and blue color. So, one solution may represent a red color graph, another values may represent a blue color graph. Then you can analyze. So, how do we obtain all those values? So, mathematically we can obtain either one set of value or two set of value or three set of values. Suppose if I want to calculate more number of values x naught, y naught, x1, y1, x2, y2 and so on up to if I want to calculate x20, y20. So, mathematically it is very difficult. So, in that case we can use some ready-made tools like MATLAB, Scilab or GeoGebra, or sometimes we can use Excel sheet or Activa. All these softwares are available, right. So, using these softwares very easily we can calculate numerical values by using fourth order RK method. Not necessarily these methods, many more methods are available, right. So, using these methods we can calculate numerical values, then you can draw the graph, right. So, I have referred internet or these websites to obtain a graph or numerical values, right. So, you can refer any physical problem. Suppose if you want to use any physical problem, so in that case you can refer these websites. So, in the next session I am going to discuss about special functions. So, we are already familiar with a differential equation with constant coefficients. We have calculated particular integral as well as a complementary function, right. So, in our particular integral may contain exponential function sin x, cos x. So, when we consider a physical problems, this type of solutions may not help us. That is why we want to go for a series solution. So, how we are going to find out a series solution? We shall discuss these things in the next session. Thank you.